Okay, we'll go ahead and get started. Distributed systems are a UX problem. My name is Tyler Treat, and I like distributed systems, which is why I helped start a consulting company that helps organizations deal with the ultimate distributed system people. We do other things, but it always seems to come back to this for some reason. So just a quick disclaimer, I know approximately nothing about UX, other than when I'm the user, I know when my experience is good and when it's bad. And so UX is one of those things I firmly believe is it's easy to tell when it's good, but it's hard to know how to actually make it good. So if you're here just to learn about like design principles or UX principles, like it's probably not the right talk. I can't really speak to that. This isn't really a UX talk per se. We're not going to talk about those kinds of things, but really it's about the intersection of systems and system design, UX, and the business. And that's really where this talk fits in. And so we'll start by talking about just that and this relationship between UX and architecture. Because there's kind of this symbiotic relationship almost. And in the early days, the way we built systems, we still build systems like this today, was as a monolith, right? And that simple client-server architecture. And it's nice, it's simple, it's easy to reason about. But as systems grow and as organizations scale, and especially as we move more things to the cloud and the elastic or dynamic nature of that, we start to move into more of this distributed world, more of this microservice world. And there's a lot of challenges and complexity that comes with that. And so I want to walk through some of the implications of moving to that more distributed type world, and using this example of a travel agent service. And so with the monolith, things were good, right? We have like our trip service, and it's backed by a database. We have that client-server interaction. And when we move to microservices, now we have like the car service, the hotel service, and the airline service. And we lose the same data semantics, same consistency semantics that we had with the monolith. Because we now have like these silos of data. We don't have that consistency that spans the entire system. And so data consistency is one of the big implications. And we also start to see some emergent behavior. Because now, a single end user request isn't just hitting like one server and giving us a response, but now it's potentially traversing a number of different services, and even in ways we didn't anticipate or expect. And so we start to see some surprising and emergent behavior, and race conditions and things like that start to crop up a little bit more. And then of course there's the performance implications, because now we're making network requests to a whole bunch of services. And then there's also this partial failure aspect, because now we have different parts of the system that are operating in various states of failure at any given moment. And so that's now something we have to think a little bit more about. And so are microservices bad? Well, no. Really, it's about people scale and how do we manage that. And certainly there are other benefits as well, but I think that's kind of the key thing. And so I want to talk about this idea of transparency within human-computer interaction, and specifically as it relates to distributed systems and to UX. And so transparency is this idea that any change in a computing system, like a new feature or a new component, is called transparent if the system after the change adheres to the previous external interface as much as possible while changing its internal behavior. So programmers might know this better as an abstraction. But the idea is we have a system, it has some inner workings, some inner mechanics, and we're able to change those without affecting the user. And so the name transparency is a little confusing because it's, the nature of it is to hide things from the user. So it seems like opacity might be a better name, but the reason we call it transparency is because the effects are transparent to the user. So it's the kind of the human angle on that. And so, for example, if I replace a single node system with a distributed system, if it's transparent, the user can't tell the difference. And so we can imagine this spectrum of transparency from low to high, and looking at a couple examples, something like NFS, networked file system, would be an example of more of a high transparency system, right? The fact that this file system is actually distributed over a network across a number of machines is entirely hidden from the user. They interact with it just like any other file system. And something like FTP is more on the low transparency end, right? In order to use it, we have to use an actual FTP client. And so those details are brought up to the surface for the user to bear. And there are a lot of different types of transparencies. We're not going to talk about these today, but things like failure transparency and location transparency and so on. And really it's about usability, and specifically this balance between usability and control. And it's this question of how much burden do we want to place on the user in order to give them that control, and how much of that burden do we want to take upon ourselves or upon the system? And so looking at another example, something like RPC, remote procedure call, would be a transparency that favors simplicity over flexibility and performance, because it provides this simple function-like interface, right? To the developer, it looks like you're just calling any other function, when in reality it's going over the network, it's talking to another machine, it's returning that result, it's handling all of that serialization, but those details are all hidden. And something like Erlang-style message passing is more of a transparency that favors things like flexibility and performance and correctness, as opposed to simplicity, because it's kind of a lower level abstraction. And so placing those on the spectrum looks something like that, approximately. And for developers, APIs are really the UX of your system. And transparencies simplify the API of a system. And so what UX is, really, is about deciding what knobs to expose. And that's the same whether you're designing an API or you're designing a user interface. And so that brings us to this balance between data consistency and UX. We talked about consistency and how that's one of the implications when we move into more of that microservice model. And so going back to our example in the days of the monolith, the good old days, we have this transparency. It's the API, or maybe it's the UI that the user interacts with. And when we move to microservices, we lose the same consistency semantics. That transparency starts to break down. It becomes kind of this leaky abstraction. And so I used to work at a company called Workiva, and they build enterprise financial reporting software. And one of their big value props is the ability to link your data. So I might have a spreadsheet with some values in it, and a Word document that links to some of those values, maybe a presentation that also links to some values. And when I change the values, those changes get propagated across all of my documents, and things stay in sync or consistent. And if we conceptualize this system as a microservice system, we can imagine something like a spreadsheet service and a document service, a presentation service, maybe an identity and access management service, and so on. But the catch with this is it's presented to the user as a single system. That's kind of the transparency that's provided. And part of that is providing data consistency, when in reality it's comprised of all of these different services. And so when we're talking about consistency, what we're really talking about is the ordering of events in a distributed system. And why is that so hard in the first place? And really what it comes down to is that there is no intrinsic ordering that we can rely on to order the events that happen within a system. And there's a very good ACMQ article by Justin Shihai called There Is No Now. And in it, he talks about just this and why specifically we can't rely on time as a way to order events across a distributed system. And really it just boils down to kind of the physical constraints that systems exist within. And so if we can't rely on time or any other property to order things, what can we do? And one of the things we can do is we can coordinate. We can impose an ordering onto the system, and we can bring all of the participants to an agreement on that ordering. And so two-phase commit is an example of this. It's a distributed transaction protocol. And so what two-phase commit does essentially is we have a transaction coordinator who's responsible for serializing the transactions within a system. So we propose a transaction and we vote on that, and then we either commit it or we abort it. But there are a number of problems with this and other related protocols, and one of which is it's a very chatty protocol. Right? There's a lot of messages going back and forth, and so it's beholden to network latency. So it has very limited throughput and limited scalability. We also have that single point of failure with the transaction coordinator. Right? If this transaction coordinator fails, then we can't process any transactions. And similarly, because it's a blocking protocol, if any one of these participants fail, then again, the system deadlocks. We can't process transactions. So like any good engineer, we fix this by adding more phases. We get three-phase commit. But this isn't really a much better alternative because it's still susceptible to a lot of the same problems, just with more messages. And so more recently, we've started to see a number of systems crop up that try to address this problem of consistency and while still remaining highly available, still remaining reasonably performant. And Google's Cloud Spanner is an example of one of those systems. And Spanner uses some specialized hardware like atomic clocks and GPS to solve this problem of time using this API that Google's built called TrueTime. And so the good news is we solved physics, but the bad news is it costs all the money. Not exactly. If you actually look at the Spanner paper and you look at the TrueTime API, what you'll see is that it doesn't solve this problem of time. What it actually does is it brings that problem to the surface. And so the TrueTime API doesn't give you back a moment in time. What it actually gives you back is a tuple. It gives you back an earliest value and a latest value. And what that tuple represents is it's a range or duration in time in which now is likely to fall within. And so what TrueTime then does is it tries to minimize that range to the point that it's actually a practical thing that we can build real systems with. And so TrueTime forces that uncertainty to the surface, and then Spanner provides a transparency over it. And so as a user of the Spanner database, I don't have to worry about the TrueTime details. And Spanner doesn't avoid the trade-offs that these other systems make. In terms of the CAP theorem, it's still a CP system. It's just that Google tried to minimize the probability of these types of problems from happening. And so Google made a business decision, essentially, that the cost of building every system in a way that handles eventual consistency outweighs the cost of trying to minimize network partitions from happening. So they made a very significant investment into their network and data center infrastructure. And the part about Spanner costing all the money, that's actually true. It's very expensive to use, and it's a proprietary system. And so people like to hold up things like Spanner and other related systems like CockroachDB is an open source database that provides similar semantics But they like to hold these up as examples of things that solve this problem of providing global consistency while remaining highly available. And that's true, but I don't think it's the end of the story. I don't think it really allows us to escape this problem of consistency within microservice systems. And the reason is, unless every service is backed by the same database, you probably still have to deal with consistency problems. And this is especially true of systems that span trust or authority boundaries, where not all parts of the system can participate in a distributed transaction. And so while things like Spanner might address this problem within the context of a distributed database, typically there's more to the story than that. And really the biggest barrier is when consistency mechanisms have to span across many stateful services, as is typically the case with microservices. And so coordination is expensive because processes can't make progress independently. And so if we have all of these services and they don't have to coordinate and check in with each other, we can have reasonably good throughput. But as soon as they have to coordinate, then that throughput goes out the window. And so this is from a talk by Peter Bayless a few years ago, and he shows just how significant that cost can be, even just going from one server to two servers that have to coordinate. We see there's almost a 400x decrease in throughput. And we haven't even talked about partial failure yet. And so what happens when we need all of these parts of the system operating in order to make progress, and one of them inevitably fails? And I'm not even talking about just kind of the UI or the UX implications of this. In the case of Netflix, if the list service goes down, hopefully I can still watch my TV shows. But what I'm really talking about is when we need all the parts of the system working in order to make meaningful progress. And so if we're not careful in how we architect our systems, we can end up with very fragile systems. And so that brings us to dealing with partial knowledge. Because really, when we're talking about partial failure, we're talking about dealing with partial knowledge. And I'm going to explain what I mean by that in just a minute. So the cost of knowing the truth can be prohibitively expensive for a lot of applications, either because throughput is constrained or the system is just fragile because we need all the parts working in order to make progress. And so if we're not careful, it also means partial failure can mean that the truth is also fragile. So where does this leave us? Well, we could punt on the problem and throw everything back into a single system and go back to the monolith and just avoid the problem, the realities of distributed systems. And this can be perfectly reasonable to do so long as we're mindful of the trade-offs. We could do what Google did and just throw a bunch of money at the problem and try to avoid, or reduce the probability of things like network partitions and these other types of partial failures. And this isn't really a realistic option, even just ignoring the financial implications, because even if we can buy servers that never fail and networks that never partition, we're still going to have code with bugs in it. And so we can't really escape the human element of that. Or we could rethink our transparencies. So we can bubble the problem up to the application UX and kind of confront the problem head on and actually change the way we design our applications. And so it can often help to look to the real world when we're thinking about loosely coupled solutions. Because in the real world, things are often inconsistent just by nature. And we find ways to deal with that. You deposit a check at the bank and the money shows up in your account 2 days later, or you coordinate dinner plans with a group of friends. If that doesn't show the cost of coordination, I probably can't think of a much better example. But rarely is the entire group on the same page, but you kind of come to an agreement or a consensus over time, hopefully. And so we allow things to be inconsistent because they just kind of inherently are, and compensate for that, as opposed to trying to prevent mistakes from happening altogether, because the cost of doing that is just usually prohibitively expensive. And a lot of accounting and finance systems have worked like that for a long time. Typically, they aren't based on consistency. They're based on auditing, compensation, and calculated risk. And accounting in particular is very much kind of rooted in the idea of an immutable ledger, and we have debits and credits, and we can reconcile that after the fact. And so there's a very good article by Gregor Hope called "Your Coffee Shop Doesn't Use Two-Phase Commit." It's kind of a famous article. And in it, he describes his experience at a Starbucks and draws parallels between how a coffee shop operates and how loosely coupled systems operate. And one of the things that he points out is that rarely do systems consist of one long synchronous interaction, but they typically consist of a sequence of short synchronous interactions with larger asynchronous things that kind of tie things together. And it's such a common pattern, in fact, that has a name called the conversation pattern. And a lot of systems work this way, right? Your Amazon shopping cart works this way. The coffee shop works this way, where you walk up to the cashier, they take your order, they place your order into a queue that the barista works off of. They compute the price, you dig up your money and you pay, they give you back your change, and then you wait for your name to be called and you pick up your drink. And so it's this series of these short synchronous interactions with that larger asynchronous interaction that's then correlated back to the synchronous part. And this gives us a number of advantages, right? We can scale different parts of this independently. We can add more cashiers, and we can add more baristas. We can handle a higher volume of transactions. But the flip side to that is we also now have a little more complexity, because different parts of the system can fail independently of each other, right? That's kind of the nature of decoupling these things. And so I want to look at a few techniques for how we can handle exceptions in asynchronous systems, because I think there's some things we can learn by looking at that. And the simplest thing we can do when something goes wrong is to do nothing, or to write off what we've already done. In the case of the coffee shop, if the customer places their order, they start making their drink, and then their credit card gets declined, maybe they just throw the drink away. And so it sounds kind of silly, but this can make a lot of sense in cases where the cost of writing it off is less than the cost of building robust error correction, or building that robust error correction reduces the throughput of the system to the point that it's no longer worth it. So writing it off can be a perfectly fine thing to do. Another thing we can do is we can retry the failed action. And this is obviously a good option if retrying it is actually likely to fix the problem. So in the case of the coffee shop, if they make the wrong drink, or they make the drink in an unsatisfactory way, then they just remake it, and hopefully that solves the problem. And the alternative to retrying is we can undo the successful action, or we can compensate. And compensating actions are especially common in monetary systems, right? Where we're dealing with money, and we can credit money that has already been debited. So if the machine breaks down and they can't make your drink, then they just refund your money. Problem solved. And so is there a way we can take some of these ideas and start to rethink two-phase commit and some of these other distributed transactions? And one of the things that we get when we do that is this idea of sagas. And sagas actually date back to the late 80s. And what a saga is, it's just a long-lived transaction that can be written as a sequence of smaller transactions. And either all of those transactions complete successfully, or compensating transactions are run to return the system to a consistent state, or to amend a partial execution. And so Saga split up this long-lived business transaction into these smaller, individual, interleaved sub-transactions. And each sub-transaction then has a corresponding compensating transaction that semantically undoes its effects. And so what sagas do is they guarantee one of two execution sequences. Either all of those sub-transactions complete successfully in the happy path case, or a subset of them complete, and then the corresponding compensating transactions are run to return it to a consistent state, to undo the effects. And so if we were to implement our travel agent system as a saga, our sub-transactions would look something like this, right? We book the flight and the hotel, the car, charge the money from the customer, and then the compensating transactions are the things that undo those effects. So we cancel the flight, cancel the hotel, cancel the car, and refund the customer their money. There's a couple things to point out with this, and one of which is compensating transactions need to be idempotent. And the reason for that is, for example, if we book the flight and that request, or if we book the flight and then book the hotel and that request fails, we'll then try to cancel the flight. And if that cancellation fails, we need to be able to retry that until it succeeds. And the other thing to point out with this is these transactions should be commutative, meaning that the order in which they execute shouldn't matter. And the reason for that is if we try to book the flight and that request times out for some reason, and then we cancel the flight, and then the original request to book it finally succeeds, we end up in an inconsistent state. We're in a situation where we intended to cancel the flight, but we ended up booking it. And so by making those commutative, we avoid any potential for inconsistency. And so what sagas do essentially is trade off isolation, I, and ACID for availability. And they give us a way to handle partial failure in a way that things like two-phase commit just don't really afford. But the trade-off with that is we kind of push that problem into the UX, because now we have to deal with that potential for lack of isolation, the implications of that. And there's also been a lot of discussion, especially at this conference, around event-driven architectures. And this can be a good alternative to more of the traditional request response type systems. There was a great talk this morning on kind of flipping request response on its head. And so moving to more of this event-driven, CQRS, et cetera, these types of architectures can be a good way to decouple systems. But it still doesn't escape that problem. And for example, each of these services probably still has its own database, whether that's a view that's materialized from some event log or it's an actual canonical database. That's still going to be something that crops up, as well as the race conditions and things like that. And so what we do when we use things like sagas and event-driven architectures is we kind of end up shifting the focus from system properties and guarantees to business rules and application invariants. Because really people don't want distributed transactions, they really just want the guarantees that distributed transactions give them. And so your customers probably don't care if you're using two-phase commit, but they probably do care if a room is double booked or some other business rule is violated. And I mentioned the CAP theorem just briefly earlier, and I wanted to talk a little bit more about this because I think it's relevant. If you're not familiar with CAP, I'll give kind of a quick synopsis. And so this was an idea originally from Eric Brewer, and it refers to these three properties of a distributed system, which is consistency, which we've talked about, availability, which is can the system respond to a request or not, and partition tolerance. Is the system susceptible to network partitions? And what the CAP theorem says, really, is when a partition happens, we have kind of one of two choices we can make. We can either choose availability and give up consistency, or we can choose consistency and give up availability. And I mean, in reality, it's more nuanced than this, but that's kind of the gist of it. For example, we could do neither of those things. And then people will also point at things like Spanner and say, well, it gives you both, but they'd be wrong. And so the CAP theorem, the reason I'm talking about this is, in reality, it's kind of a UX question. And the reason I think that is when a partial failure happens, and that's really what a network partition is, how do you want the application to respond to that? And so the kind of canonical example is the banking system, where we have an ATM and a financial institution, and occasionally the ATM gets disconnected or gets partitioned from the bank. And so if I'm trying to withdraw money and this happens, what happens? And so that's where this decision comes in, right? We can either choose consistency and sacrifice availability, in which case I can't get my money out, and the bank potentially loses out on revenue, or we can choose consistency, or choose availability rather, by making local decisions with the knowledge we have at hand and then designing the application UX accordingly. And so managing partial failure is really a matter of dealing with partial knowledge, but it's also a matter of managing risk, because in the case of the bank, rather than giving up availability and giving up potential revenue, for example, the bank manages that risk by using interest and fees and things like that. So if I overdraw my account, I'll probably get charged an exorbitant amount of interest on that overdrawn amount, as well as some additional fees tacked on top of that. And so in doing that, the bank can remain available. And so our risk appetite can really drive business rules, and it should drive business rules. For example, if we're clearing a check, the value of that check might govern which business rules we follow. For example, if it's less than $10,000, maybe we clear it locally because we're okay with that level of risk. And if it's over $10,000, maybe we double check with all the replicas before clearing it, because it's a higher level of risk, and so we're okay with paying that additional cost of coordination, of consistency, in order to manage that risk. And so Pat Helen famously describes computing as nothing more than memories, guesses, and apologies. And that's because computers operate with partial knowledge. Either there's a disconnect with the real world, or there's a disconnect between systems. And so more often than not, the system is not a perfect representation of reality. And what that means is typically systems don't make decisions, they make guesses. And those guesses might be good, they might be bad, but rarely is there certainty. And systems have memory, not in the sense of RAM, but in the sense that they remember facts and they remember guesses that they've made. And those memories help them to make better guesses in the future. And so we can store more memories at the cost of more money. We can survey other systems' memories at the cost of more latency. And the level of forgetfulness we can tolerate determines how responsive our application can be. And so that forgetfulness is also a business decision, right? It's a business decision how much money, how much latency, how much energy we're willing to put into this to reduce incorrect guesses and kind of balance that responsiveness with correctness. And sometimes the system guesses wrong. And it might mean that the business loses out on revenue or the customer loses out, but we calculate the risk of those wrong guesses and we determine when the trade-offs make sense and we compensate. And when things go wrong, we also apologize. And so systems need the capacity to apologize. And I think it's worth pointing out that customers typically judge you not by your failures necessarily, but by how you handle your failures. And so, are you building systems that never fail or systems that can fail gracefully? And I mentioned Workiva earlier. And in my time there, Workiva often maintained a net promoter score higher than Apple's. And Apple being this like the pinnacle of consumer product companies, Workiva being this enterprise software company, and here they are with a net promoter score higher than Apple's. But it wasn't because we built a perfect product or a product that never failed, as much as I would like to think that, but really because of their customer focus. And specifically by making a deliberate investment in their customer success team, who worked directly with customers and when necessary could apologize on behalf of the system. And so businesses need both code as well as people to manage those apologies, and the people part of that often gets overlooked. And so it becomes less about trying to build the perfect system and more about how we cope with an imperfect one, right? Distributed systems are as much about failure modes and recovery as they are about being operationally sound and perfectly reliable. Okay, I just want to wrap up with a few final thoughts and observations. So it can often help to look to the real world and also how things were done before computers even, when we're thinking about loosely coupled systems. And we can often find inspiration in doing that. Because the fact is life is mostly asynchronous and it's mostly inconsistent. And we find ways to cope with that and to compensate for it. And I think we also need to kind of shift our focus a little bit from these low-level system properties to higher-level business rules and application invariants. Because when we specify correctness for our application and we're thinking at this level, that's the best we can do, like ACID transactions and serializability and things like that. But that doesn't really speak to any of this stuff. And so what happens often is we kind of code our business rules and constraints into the language that our infrastructure understands. And a number of problems result from that, right? One of which is we have to be able to translate those semantics into these lower level operations, like database operations, for instance. This often precludes us from using more commodity solutions, and we end up building custom ones. There's also the performance implications, right? When this is the starting point, that's kind of the best we can do. And we could otherwise avoid a lot of those costs. And then also we put ourselves at the mercy of our infrastructure and hope it makes good on its promises. It often doesn't. And so the question then becomes, when do we actually need consistency? And this is a very active area of research, as it turns out. And there's a lot of interesting research that's looking at how to answer this question. And then also how we can kind of push things up in terms of specifying correctness into that business layer. How we can push those invariants up. And so I often come back to this parable of the car, and I first heard this idea from Chris Micklejohn. And the idea is, a car requires friction to drive, but any more friction than necessary causes inefficiencies. And so we can't eliminate it completely because it's essential to the problem, but we want to minimize it to the smallest possible contact points. And so I think a lot of these ideas are kind of similar in that sense, like consistency, for example, We can't necessarily eliminate it completely, but we want to try to minimize the need for it and avoid making that kind of the default starting point. And again, there's interesting research that's looking at how to answer that question. And so we can use consistency when the stakes are high and the cost is worth it. We can use our risk profile to determine what those stakes are and what course of action we take or what business rules we follow. And then we can design our transparencies accordingly. We can design our application UX, the application experience based on this. And so we could try to build perfect systems that never fail. We could spend a whole bunch of money and try to get the reliability we want. But really the question is, should we build perfect systems or should we build pragmatic ones? And when it comes to the business, the latter is probably the wiser choice. Because problems are rarely the problem, but coping is the problem. And so that means systems that can compensate, systems that can recover, and when needed, systems that can apologize. And that includes both code as well as people to manage those apologies. And so we have to, we can't forget to build out that part of the business and to structure things in a way that allows for that. So hopefully this gets you thinking a little bit more about these ideas and the relationships between these things. And I think they are very much kind of interconnected with each other. And if nothing else, the one thing you should take away is that these things are not just a systems problem or an engineering problem or a back-end problem. And really they kind of inform other parts of the system, right? Including how we design the UX and application experience, et cetera. And so we can't just separate those things from each other and say, okay, engineers go work on this stuff and the front end UX folks go work on this stuff. Because it's kind of one complete system. And they're really interwoven with each other. Thank you.